Hello everyone, welcome to VLSI Academy. This is Physical Design course, lecture 11, part 5 on physical design input constraints, where we shall be looking at some very important and interesting topics for those who are in academics and in professional engineering world. In previous lectures, we have briefly discussed about netlist, lefts and timing links which are needed as part of input to the physical design team. What netlist, lefts and timing lib contains and how to understand it, we have discussed that in the previous lecture, link of which is given in the description below. Today we will discuss further about another important topic, that is an input to the physical design team, and that is design constraints, which is also part of library and is needed as an input. Today we will see what type of constraints are present in the constraints file. Overall, the design constraints can be classified broadly as DRC and optimization constraints. DRC are the design rule constraints that are coming from the foundry. So these are generally fabrication lab related rules. So fabrication lab is foundry where they specify the rules which are necessary for manufacturing the chip, and generally these are either physical, so physical DRC are something which are fixed by layout team. So layout team takes care of spacing, metal spacing, or it could be metal width related, or it could be shorts, it could be opens, or it could be something which is totally layout related and physically needs to be fixed. So these constraints are taken care by physical layout team. There is timing team which takes care of logical DRCs. So logical constraints are specified in design rule constraints specification file. So logical constraints are something like, you can say, max cap. So max cap is maximum capacitance that a driver can drive. So let us take an example that if you have an inverter, how much capacitance output pin can have. This is, let's say, output pin. How much capacitance can this output pin have is specified as a maximum capacitance or maximum driving capability of the load of this pin is specified as max cap. So that is logical constraints. And then there is one more, max tran. So we know that delay is calculated with respect to these two constraints. So input pin will have your transition. So we calculate the propagation delay. We have specified this concept already in the previous lecture, that we calculate the delay of any particular cell. So that is propagation delay, and it is function of transition and output load. So input transition and output load, based on that your delay is specified. And if your output load is more or input transition is more, then your delay might not be guaranteed as per the library that this constraint is specifying. So we need to respect these constraints, otherwise we cannot guarantee the delay values, and we cannot guarantee that we are timing the design properly. Hence these constraints are very important. In fact, these constraints, input transition, not only input transition, in fact output transition is also important. Input transition, output transition, these are constraints which are necessary to be respected to ensure the proper functionality of the design, proper timing of the design. At a particular frequency it needs to match. And talking about frequency, there is one more constraint that is very important, and that is related to clock. This could be related to data and clock both. So clock and data both have capacitance and transition values which are specified in the DRC file. There is one more specifically clock related, is you have to meet the timing. So time clock period will be specified as a constraint, clock uncertainty will be specified as a constraint, and that needs to be respected. We have talked about uncertainty in detail in the STA related tutorial, and link of that tutorial, entire basic to advanced concepts are specified in that tutorial, and that link is given in the description below. You can also visit the channel and there is complete playlist of that particular series. Then comes the optimization related constraints from the designer, that has not only this timing related constraints. So you will have timing constraints in that, which are specified by the designer, which we already discussed part of it. There can be exceptions. Exceptions also we have discussed in that STA related series. Exceptions could be what is false path, that will be specified in that constraints file, what are multi-cycle path, and there are some timing critical paths which are part of half cycle. So you will have some half cycle paths, and that all is specified in that exceptions column of that particular timing constraints file. Then there could be input or output delays of the port. So input and output delays are also mentioned in this optimization related constraints file. What are input transition and output transition of the ports? In the design, all the ports will have some transition values, and that transition value will be mentioned here. This is also part of optimization related constraints. Out We are talking about transition, so there will be load also. So input load and output side load of all the ports, that will also be specified as a part of optimization constraints. Other than this also there is something which we need to which we need to optimize. So we are talking about performance of the design here. There will be optimization related to power also. So power related constraints will also be mentioned, like how much dynamic or leakage power must be respected. So dynamic or leakage power related constraints, maximum power leakage or maximum dynamic leakage or maximum leakage, these all constraints are part of your power related file. And sometimes there is one more file that is specified, and we will talk about it later on also, that is SAIF, switching activity file, that will specify how much switching activity is happening, and based on that your dynamic power optimization is done. Now let us discuss one by one what all constraints are present in SDC file. SDC is your synopsis design constraints file, which is given as a input, and this itself is actually your constraints file. So if you write in your synopsis shell, write underscore SDC and then give the file name, it will give you the synopsis design constraints file, what all it contains. So this is the constraints file exactly. And now let us see what all it contains. So it will have set max transition. It will be mentioned like this: set underscore max underscore transition and then 0.2. So if let us assume that your unit is in nanoseconds, so it means that 200 picosecond is the maximum transition for this particular clock in the clock path. So let us say that you have your clock port here and it is like this. So CLK1 is your clock port, and you are doing get underscore clocks. So you will get this clock, and in the clock path you are saying maximum transition you can have is 0.2 nanoseconds, that is 200 picoseconds. So 200 picoseconds is the maximum transition you can have in the clock path, which means let us assume if you have your clock source here, you will have a clock source. Clock port means your starting point of the clock will become this. So this is your starting point, and from here till it reaches the clock pin you will have 200 ps maximum you can have as a latency. So this is the way of specifying transition in the clock path for a particular clock. And you can also specify for a maximum transition of 200 ps get underscore clock 1 again CLKM1, but you are saying hyphen data path, which means in this particular path you can have maximum 200 ps of transition. This is the way of specifying the max tran in the data path. Then set case analysis. So if you do not know that or you want to specify, you can force a value of, let's say you have a port 1 here. So let's say this is your port 1 and you are specifying that set case analysis as 0. That means your timing will always assume a 0 pulse from this. So it is like forcing the value of some particular value to a port. If you do not have any constraint or any data coming specified coming to the port 1, you can force validate it to some value, pre-force it to some value, that is your 0 in this case. So this is also a type of case analysis, is also type of constraint which is you will find in the SDC file. You can have it in the memory pin also. So if you have some macro in the design and there will be some different pins, clock pin, data pin, memory pin. So let's say there is one pin D1 and this is the name of memory is, let's say, memory 1 itself. So how do you specify the pin? Memory 1 slash D1, and that becomes the pin of this particular memory, and you are forcing it to have a 0 value. So it will be connect, it is as good as connecting it to the ground. So tool will assume that it is connected to the ground, and then now validate the timing for this particular macro, or it could be particular design. Then you have next constraints as create clock hyphen name. So the name of the clock is CLK1, period is 10, waveform is this, and get underscore ports CLK1. So as we know that this is the CLK1 port, now we are saying that you create a clock on this port with a period of 10 nanosecond. So that means this waveform, and you are saying that first waveform is 0 and second pulse will be at, so if you have 0 here, then you are saying that your second pulse will be at 5 and it should be a period of 10, like this. This is the way of specifying the create clock command. This will create a clock and the starting point will be this CLK1 port, so it becomes your source of the clock for this particular design. Then you are saying next constraint is set input delay hyphen clock. So you are saying that this particular port, data 1 port, let's say now the port name is data 1, the port name is now, let's say, data 1, and you are saying the input delay of this particular port is 2 and associated clock will be CLK1. So it will have a timing path which is inside the design. Associated clock it will take as CLK1, and it will have an input delay of 2 nanoseconds. So it will assume that there is outside there is one virtual flop. From there till it reaches this particular port, it would have already consumed, in this path it would have already consumed 2 nanoseconds. This is a also one constraint which is specified in the library. Similar to this, there will be output constraint specified for the output port. So output delay will be specified for an output port, where it will say that until it reaches to the next flop clock pin, the total output delay it would have taken is 3 nanoseconds. So rest of the 10 out of 10 nanosecond of the clock period, you will have a 7 nanoseconds left out to optimize inside your design. That's all for this video. Please do like, share and subscribe to the channel, and do let us know your comments in the feedback section. If you want any topics to be included as a part of this series or maybe as a new topic, please do let us know through the comments or maybe in the email ID which is mentioned in the about us section. Please do share this video with the friends who are interested in taking up the VLSI as a course. That's all. Thank you.